Greetings and welcome to the Sleep with Science channel. I'm delighted you've joined us. Perhaps your day has been lengthy, or maybe you're someone who prefers drifting off while contemplating far-off worlds and wandering celestial bodies rather than tallying livestock. Regardless, this evening's voyage is designed for you. At this moment, there's nothing required of you but to relax. Allow your breathing to ease, your mind to settle, and your form to become weightless, as though the pull of gravity has released its hold, and you've started to drift peacefully through the cosmos. Tonight, our journey takes us gently across the solar system. Not along a direct route, but in gentle swirls from sun-warmed worlds and dusty orbital bands to darkened craters and icy seas locked beneath frozen shells. A narrative conveyed not through figures, but through electromagnetic tempests, askew rotations, and satellites that illuminate the darkness. From sideways rotating worlds and crystalline precipitation to primordial sunshine still traversing the emptiness, each orbital path contains something remarkable and captivating. We'll proceed slowly, calmly, just one drowsy revelation at a time. Before we start our journey, if these tranquil discoveries assist you in unwinding or provide you with a serene conclusion to your evening, please consider softly pressing the like button and joining our channel. This helps fellow explorers discover this place too, one sleepy wanderer at a time. Now, let us commence. Neptune's winds surpass sonic velocities. Though it sits as the most remote recognized planet from our star, Neptune harbors the swiftest winds within the solar system. These atmospheric currents race through its upper layers at velocities exceeding 2,000 kilometers per hour, surpassing the speed at which sound travels on Earth. That's approximately 5 times faster than a commercial aircraft cruises. The winds presumably draw their power from the planet's internal warmth, which continues to radiate outward despite the frigid temperatures at its outer layers. Neptune's gaseous envelope consists primarily of hydrogen, helium, and methane, and these winds sculpt enormous weather systems into the planet's light blue cloud formations. It's a frozen realm in perpetual supersonic movement. Mars contains a canyon spanning continental proportions, extending more than 4,000 kilometers along the Martian equatorial zone. Valles Marineris stands as the grandest canyon network in the solar system. It could stretch across the complete breadth of the United States mainland. In certain locations, it descends over 7 kilometers deep, exceeding the Grand Canyon's depth by more than 5 times. Researchers theorize it developed through a mixture of tectonic extension, volcanic forces, and surface wearing. Different from Earth's canyons, which typically form through river carving, Valles Marineris may have split open as the planet's outer layer fractured and separated. It represents a wound upon Mars' face, suggesting a turbulent geological history now preserved in frozen stillness. Venus possesses no magnetic shield. Though comparable in dimensions, mass, and makeup to Earth, Venus is missing one essential planetary characteristic: a global magnetic field. Earth's magnetic protection originates from the circulation of liquid iron in its outer core, safeguarding the planet from solar radiation. Venus, in contrast, appears to possess a sluggish or potentially solidified core, which might inhibit the type of dynamo mechanism required to generate a field. Lacking this defense, Venus's atmosphere faces constant bombardment by solar wind, which has stripped away lighter components across time. The lack of a magnetic field contributes to explaining why Venus, once potentially Earth-like, transformed into a furnace world. Crystalline carbon may precipitate on Uranus and Neptune. Far within the atmospheric layers of Uranus and Neptune, environmental conditions might be severe enough to produce something remarkable: descending diamonds. These ice giants possess substantial layers of methane gas, and under tremendous pressure and temperature, researchers theorize the methane can fragment, releasing carbon atoms. These carbon atoms subsequently compress into crystalline formations, creating minute diamonds that cascade downward toward the planetary core. Laboratory studies have replicated this mechanism, demonstrating how hydrocarbons can solidify into diamond under appropriate conditions. If this hypothesis proves accurate, then tempests of sparkling crystals might descend through the deep azure darkness of remote gas giants. Earth stands alone with plate tectonics. Among Earth's most characteristic and life-supporting attributes is its network of plate tectonics, a dynamic arrangement of shifting crustal sections that float atop the mantle. These migrating plates generate earthquakes, construct mountain ranges, and recirculate carbon dioxide, moderating the climate across geological spans. Thus far, no other planet demonstrates clear proof of this mechanism. Mars and Venus display surface fractures and volcanic characteristics, but they seem geologically inactive in comparison. Earth's plate tectonics might constitute part of what renders it habitable, propelling the long-duration cycles that stabilize temperature, maintain oceans, and facilitate the displacement of continents across eons. Certain asteroids possess their own satellites. Though we frequently envision asteroids as solitary travelers, some actually harbor moons, smaller objects circling around them. These diminutive satellites typically represent captured debris or co-formed companions. The initially discovered asteroid moon was Dactyl, which circles the asteroid Ida, unveiled by the Galileo spacecraft in 1993. Subsequently, numerous additional asteroid moon arrangements have been located, including some featuring multiple moons or peculiar binary configurations where two asteroids orbit one another. These miniature arrangements demonstrate that even in space's vastness, gravity can connect the tiniest of objects into quiet, drifting partnerships. Mercury maintains a phantom exosphere rather than a genuine atmosphere. Unlike Earth, Mercury doesn't retain a dense atmosphere to preserve heat or disperse light. Rather, it possesses a delicate, tenuous layer of particles designated an exosphere, a near vacuum where atoms bounce about without interaction. This exosphere comprises atoms ejected from the surface by solar wind and micrometeoroid collisions, containing sodium, potassium, and oxygen. Since Mercury lacks sufficient gravity to maintain a real atmosphere, these particles continuously flee into space and get replenished from the surface. The outcome is a ghostly, shimmering covering of dispersed atoms, imperceptible to vision, but discoverable with appropriate instruments. Our star sheds millions of tons of matter every second. Each second, the sun transforms over 4 million tons of its own substance into energy through nuclear fusion. Within its core, hydrogen atoms fuse into helium, emitting light and warmth that energizes our solar system. This energy spreads outward in every direction, heating planets, propelling winds, and sustaining life on Earth. Although the loss seems minuscule relative to the sun's complete mass, across billions of years it accumulates. Ultimately, the sun will deplete its hydrogen supply and begin to transform. But presently, it persists in burning steadily, surrendering a minute portion of itself with each passing second. Saturn's rings gradually vanish. The magnificent rings encircling Saturn aren't everlasting. They're progressively descending into the planet, attracted by gravity and drawn down by Saturn's magnetic field. This mechanism, termed ring rain, entails streams of ice particles and charged substance drifting inward across time. Data from the Cassini spacecraft indicates that the rings might be younger than 100 million years old, youthful by planetary measures, and could disappear completely in another few 100 million years. Though they appear eternal, Saturn's rings constitute a transient feature, a glittering spectacle that will someday fade into history. Mars undergoes planet-encompassing dust tempests. Mars is renowned for its rust-colored desert-like terrain and for the enormous dust storms that occasionally blanket the complete planet. These storms can persist for weeks or even months, obscuring sunlight and restructuring the surface. The dust is remarkably fine and can remain suspended in the atmosphere, producing a hazy reddish luminescence. Some storms initiate as minor gusts, but can expand rapidly due to feedback mechanisms between warmth, wind, and landscape. In 2018, such a storm resulted in the conclusion of the Opportunity rover's mission, as its solar panels began choked with dust. Even lacking rain or oceans, Mars remains a dynamic and turbulent world. Europa might harbor a saline ocean underneath its ice. Beneath the frozen exterior of Jupiter's moon Europa, robust evidence exists for an extensive subsurface ocean of liquid water. Tidal forces from Jupiter's gravity flex Europa's interior, producing heat that might prevent the ocean from freezing solid. The surface displays dark lines and ridges, indications of shifting ice, and spacecraft have identified magnetic patterns and chemical traces that validate the ocean theory. What renders Europa particularly captivating is the prospect that this concealed sea could shelter life. It's a dark, alien ocean, warmed from beneath, enclosed beneath ice, yet potentially abundant with components for biology. Mars harbors a volcano surpassing Everest in height. Olympus Mons, the most elevated volcano in the solar system, rises nearly 22 kilometers above the Martian plains, almost 3 times Mount Everest's elevation. It's so expansive that it could blanket the complete state of New Mexico. Formed by repeated eruptions spanning millions of years, Olympus Mons achieved such magnitude partly because Mars lacks plate tectonics. On Earth, volcanic hotspots migrate over time, forming chains of islands like Hawaii. But on Mars, the crust remains stationary, permitting magma to erupt in the identical location repeatedly. The outcome is a solitary massive shield volcano that towers silently in the Martian night. Saturn's rings measure paper-thin. Saturn's majestic rings extend more than 280,000 kilometers across, yet they're astonishingly slender. In most locations, the rings measure less than 100 meters thick, thinner than numerous city structures. Composed mostly of water ice, the ring particles vary in dimension from dust grains to house-sized boulders. When sunlight traverses the ring zone, they nearly vanish from view like a pane of glass rotated sideways. Their flatness is preserved by the planet's gravity, the self-arrangement of billions of icy fragments, and the effect of small shepherd moons. From afar, they seem solid, but up close, they're fragile and ethereal. Earth ranks as the densest planet. Among all planets in the solar system, Earth is the densest, meaning it compresses more mass into each cubic centimeter than any other planet, attributable to its composition of metal-rich core and silicate mantle. Earth's density measures approximately 5.5 grams per cubic centimeter, exceeding that of Jupiter, despite the gas giant's far superior size. This high density fulfills a crucial role in producing Earth's magnetic field, which originates from the circulation of molten iron in its outer core. Our planet's internal arrangement is compact, heavy, and stratified, shaping not merely its gravity, but its geology and protection from space. The sun oscillates like a musical instrument. Though inaudible to our ears, the sun constantly resonates with pressure waves that undulate through its blazing layers. These oscillations, produced by ascending and descending currents of plasma, generate ultra-low frequency sounds far beneath human hearing. Scientists examine these vibrations through a method called helioseismology. By monitoring how the waves propagate and rebound within the sun's body, researchers can chart its internal architecture, much like geologists employ seismic waves to investigate Earth's interior. These solar songs unveil hidden flows, magnetic activity, and the dynamics of fusion deep within the core. In a manner, the sun constantly hums, quietly revealing its secrets through oscillation and rhythm. Venus rotates in reverse. Unlike most planets in the solar system, Venus spins in the contrary direction, a phenomenon designated retrograde rotation. On Venus, the sun ascends in the west and descends in the east. Even more peculiar, its rotation is remarkably sluggish. A solitary day on Venus endures longer than its year, requiring 243 Earth days to accomplish one rotation. Scientists remain uncertain why this occurred, but one hypothesis is a colossal collision early in its history that modified its spin. Another theory proposes tidal interactions with the Sun gradually inverted its axis across time. Regardless of the cause, Venus stands alone as a slow-turning world with a reversed rhythm. Jupiter possesses more than 90 moons. The gas giant Jupiter isn't merely the most massive planet. It's also the sovereign of moons. Currently, astronomers have cataloged over 90 natural satellites circling it, and new ones continue being discovered. Its four most massive moons, Io, Europa, Ganymede, and Callisto, are designated the Galilean moons, named for Galileo Galilei, who initially observed them in 1610. But beyond these giants exists a swarm of smaller, irregular moons, many captured from passing objects. Some circle backward, some measure just a few kilometers across. Combined, they constitute a miniature solar system in orbit around Jupiter, bound by the planet's immense gravity and history. Mercury conceals ice within its shadows. Scorching during daylight and freezing at night, Mercury isn't where one would anticipate discovering ice. Yet it's present. At its poles, deep within craters that never receive sunlight, temperatures remain cold enough for water ice to persist. These permanently shadowed zones function like natural freezers, preserving ice for millions of years. Radar reflections from spacecraft like Messenger have verified the presence of these bright, icy deposits. Scientists theorize the water might have arrived from comet impacts or ancient volcanic outgassing. In the center of one of the warmest planets, ice survives, imprisoned in darkness, protected by crater walls from the unrelenting solar blaze. Pluto's heart might conceal an ocean. The luminous heart-shaped feature on Pluto, designated Sputnik Planitia, isn't simply a scenic landmark. It might be the surface manifestation of a vast underground ocean. Though Pluto lies distant from the Sun and cold enough to freeze nitrogen, evidence from the New Horizons spacecraft proposes that a stratum of liquid water might lie underneath its icy crust. The weight of the heart-shaped basin and its evident geological activity suggest a slushy, convecting subsurface. If this ocean exists, it could be maintained liquid by heat from radioactive decay and insulating ice layers above. Even in the frozen reaches beyond Neptune, a hidden sea might quietly persist. The asteroid belt comprises mostly vacant space. Despite popular imagination, flying through the asteroid belt wouldn't resemble dodging rocks in a science fiction movie. In reality, the belt is extensive and sparsely populated. Situated between Mars and Jupiter, it contains millions of rocky bodies, but they're separated by enormous distances. A spacecraft passing through would almost never encounter an obstacle. The complete mass of the asteroid belt is less than 5% that of the Moon. Its largest members like Ceres and Vesta account for most of that. The remainder are scattered fragments from the early solar system, ancient building blocks that never coalesced into a planet. Uranus rolls around the Sun. Most planets spin like tops, tilted slightly on their axis. But Uranus is tipped so extremely that it essentially rolls along its orbital path with an axial tilt of 98 degrees. This signifies its poles point almost directly at the Sun during portions of its orbit, giving it extreme and bizarre seasons. Each pole undergoes 42 years of daylight, followed by 42 years of darkness. The origin of this tilt remains debated, but it may have been knocked sideways by a massive collision long ago. Uranus's tilted orientation gives it one of the strangest climates in the solar system. Jupiter's radiation belts prove lethal. Jupiter is encompassed by a massive magnetic field, the most powerful of any planet, and within it are radiation belts so intense they would obliterate unprotected spacecraft in hours. These belts are filled with charged particles trapped by the planet's magnetic field. forming zones of high-energy radiation similar to Earth's Van Allen belts, but vastly more powerful. Jupiter's largest moons are exposed to this radiation too, which can affect their surfaces and potential habitability. To survive in orbit around Jupiter, spacecraft must employ special shielding measures or remain in low radiation paths. It's a magnificent world, but one wrapped in invisible danger. The Sun holds nearly all the mass in the solar system. At the heart of our solar system, the Sun dominates not just with light and gravity, but with sheer mass. It contains over 99.8% of all the mass in the solar system. That signifies everything else, all the planets, moons, asteroids, comets, and dust comprises less than 1/4%. Its gravitational pull binds everything in orbit, from tiny grains in the asteroid belt to distant comets in the Oort cloud. This immense mass is what fuels the fusion reactions at its core, converting hydrogen into helium and flooding space with the energy of daylight. More dwarf planets exist than classical planets. Beyond Neptune lies a scattered population of icy, distant objects, many of which are substantial enough to qualify as dwarf planets. Pluto is the most renowned, but it's just one among many. Others like Eris, Haumea, and Makemake share this status, and more candidates are constantly being discovered in the Kuiper Belt and beyond. In fact, the number of dwarf planets may vastly exceed that of the 8 classical planets. These small round worlds are relics of the early solar system, untouched and ancient. Though they orbit in the cold shadows, they hold clues to the formation of everything we know. A day on Venus surpasses its year in length. Venus has one of the slowest rotations of any planet. It requires 243 Earth days to spin once on its axis. Meanwhile, it only requires 225 days to complete one orbit around the Sun. That means a single day on Venus from one sunrise to the next is actually longer than a full year. This sluggish spin also contributes to extreme surface conditions, with temperatures hot enough to melt lead. Combined with its thick, acidic atmosphere and crushing pressure, Venus is a world of slow, simmering heat and eerie sunless days. Titan harbors lakes composed of methane. Saturn's largest moon, Titan, is the only other location in the solar system known to have stable liquids on its surface, but they're not composed of water. Instead, Titan's lakes and rivers consist of liquid methane and ethane flowing across a landscape sculpted by cold chemistry. Its thick atmosphere, rich in nitrogen, forms weather systems that include methane rain and even seasonal storms. Some of Titan's lakes are vast, extending hundreds of kilometers. Beneath the icy surface, scientists believe a subsurface ocean of water may also exist. Titan is a world with familiar shapes, clouds, rivers, coasts built from alien substances. The moons of Mars might be captured asteroids. Mars has 2 tiny misshapen moons, Phobos and Deimos. They resemble asteroids more than traditional moons, irregular, rocky, and pockmarked with craters. Many scientists believe they were once part of the asteroid belt and were captured by Mars's gravity long ago. Their strange orbits and low densities support this idea, though some alternative theories suggest they may have formed from debris after a massive impact. Phobos is slowly spiraling toward Mars and will eventually break apart or crash into the planet. Deimos is drifting away. These little moons are quiet passengers in orbit, remnants of a chaotic past. Jupiter radiates its own heat. Unlike most planets, Jupiter emits more energy than it receives from the Sun. This internal glow comes from leftover heat from its formation, a kind of gravitational energy released when the planet's immense mass collapsed together. Over time, it continues to contract slightly, generating heat in the process. This warmth drives Jupiter's turbulent weather systems, including its giant storms and swirling bands. In the infrared spectrum, Jupiter shines brightly like a smoldering coal beneath cloud layers. It's not a star, but it almost became one. If it had been just a bit more massive, it could have ignited into a failed sun. Neptune was discovered through mathematics. Unlike other planets, Neptune wasn't discovered by simply looking through a telescope. Instead, astronomers noticed irregularities in Uranus's orbit, tiny deviations that couldn't be explained by known gravity. Two mathematicians working independently in the 1840s used these strange motions to predict the location of a hidden planet. When astronomers pointed their telescopes toward the calculated position, Neptune was there. It was a triumph of celestial mechanics, confirming that unseen forces could be mapped through mathematics alone. Neptune was the first planet found on paper before it was seen through glass, a world brought to light by numbers. Saturn's North Pole displays a hexagon. At Saturn's North Pole, a massive cloud pattern spins in the shape of a nearly perfect hexagon. This six-sided jet stream spans over 30,000 kilometers across wider than Earth and has persisted for decades, possibly centuries. Scientists believe the hexagon forms from the way Saturn's atmosphere rotates and interacts with stable waves of air trapped around the pole. In laboratory experiments, similar shapes appear when rotating fluids at different speeds. The fact that such a geometric shape can emerge naturally in a planetary atmosphere is still one of the more surreal and elegant phenomena in the solar system. The Sun's atmosphere exceeds its surface in temperature. It might seem intuitive that the hottest part of the Sun would be its surface, but it's not. The visible surface, or photosphere, has a temperature of about 5,500 degrees Celsius. Yet the outer atmosphere, known as the corona, can reach over 1,000,000 degrees. This unexpected increase in temperature has puzzled scientists for decades. One theory suggests that magnetic waves from deep within the Sun transfer energy upward and heat the corona from below. Another possibility involves tiny solar explosions called nanoflares. Either way, the Sun's outer layers glow with mysterious searing heat far beyond their source. The Kuiper Belt is full of icy worlds. Beyond Neptune lies a wide ring of icy objects known as the Kuiper Belt. It stretches billions of kilometers from the Sun and is home to countless frozen bodies, including Pluto, Eris, Haumea, and Makemake. These are not stars or planets, but ancient remnants from the solar system's formation. Some are spherical and classified as dwarf planets, while others are irregular, tumbling through space. The Kuiper Belt is similar in structure to the asteroid belt, but it's far colder and contains more primordial ice. It's a fossil zone, a frozen archive of the materials that built the outer worlds. The Oort cloud may stretch a light year from the Sun. Far beyond the Kuiper Belt, even beyond Pluto's furthest reach, lies a hypothetical shell of icy bodies known as the Oort cloud. Though never directly observed, this vast sphere of frozen debris is thought to encircle the solar system and extend nearly a light year away. It's the likely source of long-period comets, which appear from the depths of space with unpredictable orbits. These distant objects are only weakly bound to the Sun, and a passing star or galactic tide could send one hurtling inward. If the Oort cloud exists, it marks the true edge of the Sun's gravitational influence, a distant halo of icy wanderers. Io is the most volcanic world in the solar system. Jupiter's moon Io is a seething, restless world covered in active volcanoes. Its surface is constantly reshaped by eruptions of molten sulfur and rock, painting the landscape in vivid yellows, reds, and blacks. Some volcanic plumes rise hundreds of kilometers into space. This extreme activity is driven by tidal heating. Io is squeezed and stretched by Jupiter's gravity along with gravitational tugs from neighboring moons. The friction from this constant flexing heats the interior, powering its furious geology. Unlike Earth's cooling crust, Io's surface is young, volatile, and ever-changing, a lava-lit moon with a molten heart. Triton orbits backward around Neptune. Triton Neptune's largest moon is unique among large moons because it orbits its planet in the opposite direction of Neptune's rotation, a motion called retrograde orbit. This backward path suggests Triton did not form alongside Neptune, but was likely captured from the Kuiper belt. That capture may have caused dramatic upheaval, potentially disrupting Neptune's original satellite system. Triton is also geologically active, with cryovolcanoes that spew icy material into space and a thin atmosphere that drifts in and out with the seasons. Cold, distant, and moving in reverse, Triton is a world that defies expectations at every turn. Earth's moon is unusually large. Compared to the size of its host planet, Earth's moon is enormous. No other rocky planet in the solar system has such a relatively large satellite. In fact, the moon is about 1/4 the diameter of Earth, a ratio more typical of dwarf planet-moon systems than full-sized planets. Most scientists believe the moon formed after a Mars-sized body collided with the young Earth, ejecting debris into orbit that eventually coalesced into the moon. This close partnership has profoundly influenced Earth's tides, climate, and stability over billions of years. Our moon isn't just a companion. It's a cosmic legacy of planetary collision and renewal. Planetary orbits aren't perfect circles. Although we often imagine the planets moving in perfect circular paths around the Sun, their orbits are actually ellipses, slightly stretched circles with the Sun offset from the center. This elliptical shape means that each planet has a point where it's closest to the Sun called perihelion, and a point where it's farthest called aphelion. For most planets, the difference is subtle, but for others like Mercury and Pluto, it's more dramatic. These variations influence seasons, solar radiation, and orbital speed. The elliptical nature of planetary motion was first described by Johannes Kepler in the 1600s, reshaping our understanding of the solar system's elegant mechanics. Some comets come from the edge of interstellar space. Long-period comets, the kind that appear only once every few thousand years, are believed to come from the Oort cloud, a distant shell of icy debris that may lie nearly a light-year from the Sun. These comets travel on elongated, loosely bound orbits and are often dislodged from their resting places by passing stars or galactic tides. When they fall inward toward the Sun, they can light up with spectacular tails, visible even from Earth. Some may have spent billions of years drifting in darkness before being nudged into motion. Their bright returns are fleeting glimpses of the solar system's most ancient, untouched matter. The Sun will become a white dwarf. The Sun, like all stars, has a finite lifetime. In about 5 billion years, it will exhaust the hydrogen fuel in its core and expand into a red giant, engulfing the inner planets. After shedding its outer layers in a glowing shell of gas called a planetary nebula, the core that remains will become a white dwarf, a dense Earth-sized remnant made mostly of carbon and oxygen. This white dwarf will no longer produce energy, but will slowly cool over trillions of years. It will be the final form of our Sun, a glowing ember in the darkness, marking the end of its stellar journey. Mars has seasons like Earth. Though it is colder and thinner in atmosphere, Mars experiences seasons much like our own planet. This is because Mars has a similar axial tilt, about 25 degrees, compared to Earth's 23 degrees. As it orbits the Sun, this tilt causes sunlight to strike different hemispheres more directly at different times of year. The result is a cycle of spring, summer, autumn, and winter, with varying temperatures and light. Martian seasons also influence polar ice caps, dust storms, and even subtle changes in air pressure. They unfold more slowly than on Earth, however, because Mars takes nearly twice as long to complete a year. Ganymede is the largest moon in the solar system. Jupiter's moon Ganymede is the largest natural satellite in the solar system, even bigger than the planet Mercury. With a diameter of over 5,000 kilometers, Ganymede has a rocky core, a possible subsurface ocean, and a crust covered in ridged ice and ancient scars. Uniquely, it is the only moon known to have its own magnetic field, which creates shimmering auroras in its thin atmosphere. Scientists believe Ganymede may have multiple layers of ocean sandwiched between sheets of ice, forming a complex internal world. Despite its size and richness, it remains quiet and dark, orbiting deep within Jupiter's magnetic grasp. Pluto sometimes orbits closer to the Sun than Neptune. Although Pluto is usually the most distant of the classical or dwarf planets, its orbit is highly elliptical, meaning it sometimes travels closer to the Sun than Neptune. This last occurred between 1979 and 1999, when Pluto was temporarily the 8th planet from the Sun instead of the 9th. Even so, the two worlds never collide or come dangerously close because their orbits are in resonance. For every 3 orbits Neptune makes, Pluto completes exactly 2. This gravitational choreography keeps them in a stable dance, with their paths never crossing. It's a delicate balance governed by celestial rhythm and time. The Sun reverses its magnetic field every 11 years. Roughly every 11 Earth years, the Sun's magnetic field flips. The north and south magnetic poles switch places. This process, known as the solar magnetic cycle, is tied to the Sun's internal dynamics and affects solar activity, including sunspots, flares, and coronal mass ejections. At the peak of the cycle called solar maximum, the Sun is more active, with more intense radiation and magnetic storms. As the cycle wanes, activity decreases, eventually reaching solar minimum. These cycles influence Earth's upper atmosphere, satellites, and even auroras. The Sun's magnetism is not fixed, but pulses and flows like a breathing magnetic heartbeat. Planetary alignments don't cause natural disasters. It's a common myth that planetary alignments can trigger earthquakes, floods, or other major disasters on Earth. But there's no scientific evidence for such effects. The gravitational pull of other planets on Earth is minuscule compared to the Moon or the Sun. Even during rare alignments, their combined influence is negligible. The Moon, being so close, has far more impact on tides and seismic stress than massive but distant planets like Jupiter or Saturn. Planetary alignments are beautiful and mathematically interesting, but they're gravitationally harmless. A silent dance of distant worlds, not a celestial omen. Leaving the solar system takes decades. Escaping the pull of the Sun is no small task. Spacecraft like Voyager 1 and 2, launched in the 1970s, have only recently entered interstellar space, the region beyond the heliopause where solar wind gives way to the interstellar medium. These missions took more than 40 years to reach that boundary, traveling outward at speeds over 60,000 kilometers per hour. The Voyager probes have crossed the orbits of the planets, passed through the Kuiper Belt, and continued into the dark. They carry instruments still functioning, as well as a golden record filled with sounds of Earth. They are our quiet ambassadors to the galaxy. Earth's magnetic field shields us from space radiation. Surrounding our planet is an invisible magnetic field generated by the movement of molten iron in Earth's outer core. This magnetic field deflects charged particles from the Sun, protecting the atmosphere and surface from harmful solar and cosmic radiation. Without it, the solar wind would gradually erode our atmosphere, as it likely did on Mars. The field also funnels some particles toward the poles, where they interact with atmospheric gases and produce auroras, shimmering curtains of green, red, and violet light. Earth's magnetosphere is a dynamic shield, essential for preserving both life and climate over geological time. The Moon is slowly moving away from Earth. Each year, the Moon drifts about 3.8 centimeters farther from Earth. This slow retreat is caused by tidal interactions. The gravitational pull between Earth and the Moon creates bulges in our planet's oceans, which in turn push the Moon slightly outward. In the distant past, the Moon was much closer and appeared significantly larger in the sky. As it recedes, our days gradually lengthen, and eclipses become less frequent and dramatic. Billions of years from now, the moon's orbit will be so wide that total solar eclipses will no longer be possible. The sky is changing, even if we don't yet feel it. The Kuiper Belt holds icy worlds with mirrored surfaces. Far beyond Neptune, the Kuiper Belt contains not only dwarf planets, but also smaller icy bodies with startlingly bright surfaces. One example is Haumea, a fast-spinning, football-shaped object coated in crystalline water ice. Another, Eris, reflects nearly all the sunlight that hits it, making it one of the most reflective bodies in the solar system, brighter than freshly fallen snow. These objects may have been resurfaced by cryovolcanism, impacts, or chemical interactions. In the darkness at the edge of the sun's reach, some of these distant worlds gleam like cold mirrors, catching faint sunlight in their frozen silence. Enceladus sprays water into space. Saturn's tiny moon Enceladus may be small, but it hides a spectacular secret. From its south pole, towering geysers of water vapor and ice crystals erupt into space through cracks known as tiger stripes. These plumes are powered by tidal heating beneath the surface, where friction caused by Saturn's gravitational pull keeps a subsurface ocean in a liquid state. The material in the plumes contains organic compounds, salts, and even signs of hydrothermal activity, raising the tantalizing possibility of life. Some of the water escapes into space and helps replenish Saturn's E-ring, creating a living connection between moon and planet. Some asteroids are just piles of rubble. Not all asteroids are solid rock. Many are loose collections of stones, gravel, and dust held together only by gravity, structures known as rubble piles. These fragile bodies can form after collisions shatter larger asteroids, with the debris slowly coming back together over time. Rubble pile asteroids can have large internal voids, spin strangely, and change shape under pressure. Missions like Hayabusa 2 and OSIRIS-REx have visited such bodies, confirming their delicate, porous nature. These asteroids are not monolithic relics, but chaotic assemblages, ancient drifting ruins of early planetary construction that barely hold themselves together as they orbit the Sun. Mercury's core is disproportionately large. Mercury is a small planet, but it has an unusually massive iron core. This metallic center makes up about 80% of the planet's radius, a far larger proportion than seen in Earth or Venus. The reason for this oversized core remains uncertain. Some scientists think Mercury once had a thick rocky mantle that was stripped away by a giant impact. Others believe it formed close to the Sun, where solar forces favored the accumulation of heavier elements. The result is a planet with a thin crust, a huge core, and a weak magnetic field, a metal-heavy survivor from the solar system's chaotic youth. Venus has no moons at all. Among the rocky planets, only Mercury and Venus are without natural satellites. While Mercury's proximity to the Sun may explain its lack of moons, Venus's situation is more puzzling. It's roughly the same size as Earth, which has a large moon, yet Venus has none. Some theories suggest it may have once had a moon that fell back into the planet or was lost in a collision. Others argue that Venus's slow retrograde rotation might prevent stable orbits from forming. Whatever the cause, Venus orbits alone, a bright, cloud-wrapped world with no lunar companion in its twilight sky. Most of the solar system's moons orbit gas giants. While Earth has just one moon and Mars has two tiny ones, the giant planets of the outer solar system are surrounded by sprawling systems of satellites. Jupiter and Saturn each have dozens of confirmed moons, ranging from tiny captured asteroids to massive worlds like Ganymede and Titan. Uranus and Neptune also host many icy moons, some with complex orbits and hidden oceans. These gas giants act like miniature solar systems, their gravity drawing in debris and coalescing satellites over time. The farther from the Sun you go, the more moons you'll find, a reminder that gravity gathers companions in the cold. Hubble has photographed planets from Earth orbit. Though it orbits just above Earth, the Hubble Space Telescope has captured detailed images of the outer planets, including cloud bands on Jupiter, storms on Neptune, and seasonal changes on Mars. These images provide long-term observations that complement spacecraft flybys, offering views of evolving weather patterns, ring systems, and planetary auroras. Hubble's clarity allows scientists to track storm development, monitor impact events, and study atmospheres in ultraviolet and visible light. From its quiet perch in low Earth orbit, Hubble watches not only the distant galaxies, but also the shifting faces of our neighboring worlds. Jupiter's Great Red Spot is centuries old. The Great Red Spot is a massive storm swirling in Jupiter's southern hemisphere, wide enough to swallow 2 or even 3 Earths. It has been raging for at least 350 years, possibly much longer. First observed in the 1600s through early telescopes, the storm has changed over time, gradually shrinking, but still remaining powerful. Its reddish hue may be caused by complex chemical reactions in Jupiter's atmosphere, triggered by sunlight and high-altitude compounds. Wind speeds exceed 400 kilometers per hour along its outer edges. While Earth storms last days or weeks, this Jovian tempest spans centuries, trapped in the planet's turbulent belts. Neptune radiates more heat than it receives from the Sun. Although it lies far from the Sun, Neptune is not a frozen, inert world. In fact, it radiates about 2.6 times more energy than it receives. This internal heat drives strong winds and storm systems, including the fastest recorded winds in the solar system. The exact source of Neptune's heat remains uncertain, but possibilities include residual energy from its formation, slow gravitational contraction, or radioactive decay within its core. Despite its extreme distance, Neptune is a world of surprising energy, a planet with a cold exterior and a warm, restless interior, constantly reshaping its windswept atmosphere. Earth is the only planet with water in all 3 states. Our planet is unique in that water exists naturally on its surface as a solid, liquid, and gas. Ice caps and glaciers, oceans and lakes, clouds and vapor, all coexist and cycle through the atmosphere, land, and sea. This balance is crucial for life and is regulated by Earth's distance from the Sun, its atmospheric pressure, and its relatively stable climate. Other worlds may have water in isolated forms, icy crusts, vapor in thin atmospheres, or hidden subsurface oceans, but none show the same dynamic planet-wide presence. On Earth, water flows, freezes, and evaporates in a never-ending, life-sustaining dance. The heliopause marks the edge of the Sun's influence. As the solar wind flows outward from the Sun, it eventually collides with the interstellar medium, the thin gas and dust between stars. This boundary is called the heliopause, and it defines the outer edge of the Sun's protective bubble, known as the heliosphere. Beyond this point, the pressure from other stars and galactic particles becomes stronger than the solar wind. Voyager 1 crossed the heliopause in 2012, followed by Voyager 2 in 2018, entering true interstellar space. Though the Sun's gravity still extends much farther, the heliopause marks the end of its energetic reach, the final breath of solar influence before deep space begins. The solar system is drifting through a local cloud. Our entire solar system is moving through a region of space called the local interstellar cloud, a thin concentration of gas and dust about 30 light-years across. It's part of a larger structure known as the local bubble, formed by ancient supernova explosions. As the Sun travels through this cloud at about 70,000 kilometers per hour, its heliosphere acts like a shield, deflecting interstellar material. Scientists study this cloud to understand how interstellar conditions can affect cosmic rays, the heliosphere's shape, and even climate on Earth. We are not sitting still in space. We are sailing slowly and silently through a galactic fog. Some moons are geologically active. Activity is not limited to planets. Several moons in the solar system show signs of internal energy and surface change. Io, a moon of Jupiter, is riddled with active volcanoes fueled by tidal heating. Enceladus, orbiting Saturn, vents plumes of water vapor into space. Europa and Ganymede likely have subsurface oceans stirred by internal warmth. Even distant Triton, Neptune's captured moon, shows signs of cryovolcanism, icy eruptions driven by shifting pressures below. These moons are not static ice balls. They are restless worlds with geology, chemistry, and perhaps even the potential for biology hidden beneath their frozen exteriors. Pluto's atmosphere comes and goes. Though Pluto is small and cold, it has a thin atmosphere composed mostly of nitrogen, with traces of methane and carbon monoxide. When Pluto approaches the Sun in its elliptical orbit, surface ices sublimate into gas, forming a hazy envelope that expands into space. But as it moves farther out, the atmosphere cools and collapses, freezing back onto the surface like frost. This cycle repeats over Pluto's 248-year orbit. During the New Horizons flyby in 2015, Pluto's atmosphere was visible as a layered blue haze, a fleeting breath of warmth around a world that spends most of its time in deep cosmic winter. Temperatures at the Sun's core exceed 15 million degrees. Deep inside the Sun, at its center, temperatures soar to over 15 million degrees Celsius. Here, hydrogen atoms are compressed under immense pressure until they fuse into helium, releasing enormous amounts of energy in the process. This fusion is what powers the Sun's light and heat, and ultimately all life on Earth. The energy generated in the core takes hundreds of thousands of years to reach the surface, bouncing through layers of dense plasma. Once it escapes, it travels across space in just over 8 minutes to reach us. The Sun's radiant calm hides an unimaginably hot and violent heart. Uranus has a faint, tilted ring system. Though Saturn's rings are the most iconic, Uranus also has rings 13 known ones. In fact, though they are much darker and fainter. Made of tiny particles of rock and ice, these rings orbit in alignment with Uranus's unusual tilt. Since the planet lies almost on its side, the rings appear vertical when viewed from above the Sun's north pole. Some of the rings are narrow and sharp-edged, possibly shaped by small moons that shepherd their structure. They weren't discovered until 1977, when they blocked the light of a background star. They are subtle, shadowy bands circling the sideways planet. The heliosphere is a magnetic bubble blown by the Sun. The solar wind, a stream of charged particles released by the Sun, flows outward in all directions, forming a vast magnetic bubble around the entire solar system. This structure is called the heliosphere, and it acts like a shield against galactic radiation. Shaped by solar activity and interstellar pressure, it stretches far beyond Pluto, enclosing the planets, comets, and distant objects. Its outer edge, the heliopause, is where solar influence fades. As the Sun orbits the Milky Way, the heliosphere moves with it, protecting the solar system as it drifts through changing regions of interstellar space. Mercury's orbit helped prove Einstein's theory of gravity. For centuries, astronomers noticed something strange about Mercury's orbit. Its closest approach to the Sun, called perihelion, slowly shifted over time more than Newtonian physics could account for. In 1915, Albert Einstein's theory of general relativity provided the solution. According to relativity, massive objects like the Sun warp the fabric of spacetime, subtly altering planetary paths. The small but measurable effect on Mercury's orbit matched Einstein's predictions exactly. This became one of the first experimental confirmations of his revolutionary theory, a triumph of mathematics explaining a quirk in the motion of a scorched rocky world. The Moon shapes Earth's tides. The daily rise and fall of ocean tides on Earth are largely caused by the gravitational pull of the moon. As the moon's gravity tugs on Earth's oceans, it creates bulges on the side, facing the moon and the opposite side. As Earth rotates, these bulges move across the globe, producing high and low tides. The sun also influences tides, creating spring and neap tides depending on its alignment with the moon. Tidal forces not only affect oceans, but can also subtly shift the Earth's crust and even influence the rotation of the planet itself. The moon's silent pull keeps the oceans in motion. There may be undiscovered planets beyond Neptune. Astronomers have noticed that some distant objects in the Kuiper belt follow clustered, elongated orbits that can't be easily explained by the known planets. One leading theory is that a large, as yet undetected planet, sometimes called Planet 9, may be influencing these distant paths with its gravity. If it exists, this hidden planet would be several times the mass of Earth and orbit far beyond Pluto, taking thousands of years to complete a single revolution. No direct evidence has yet confirmed it, but telescopes are searching. If found, it would reshape our understanding of the solar system's outer architecture. Callisto may have an ocean beneath its icy surface. Jupiter's moon Callisto appears quiet and cratered, with an ancient surface untouched by recent geological activity. But deep beneath that frozen crust, scientists suspect a subsurface ocean may exist, kept liquid by internal heating and perhaps residual heat from formation. Magnetic readings from the Galileo spacecraft hinted at a conductive layer beneath the surface, consistent with salty water. If confirmed, Callisto would join Europa and Ganymede as another ocean world. Though less well known, Callisto's deep, dark sea could contain ingredients for life, silently sealed beneath a shell of ice and time. Venus is hotter than Mercury, despite being farther from the Sun. Although Mercury is the closest planet to the Sun, Venus holds the record for the hottest surface temperatures. This is due to its incredibly thick atmosphere, composed mostly of carbon dioxide, which traps heat in a runaway greenhouse effect. Surface temperatures on Venus exceed 460 degrees Celsius, hot enough to melt lead. The dense clouds reflect sunlight, but they also prevent heat from escaping. Meanwhile, Mercury, with its thin exosphere, has no such insulation and cools rapidly on its dark side. Venus's searing heat isn't just about proximity to the Sun. It's about atmosphere and the power of trapped radiation. The rings of Saturn are made mostly of ice. Though they shimmer like solid bands, Saturn's rings are composed of countless individual particles, mostly water ice ranging from grains of dust to chunks the size of houses. These icy fragments orbit in an incredibly thin, flat disk, kept in place by Saturn's gravity and the influence of nearby moons. The ice gives the rings their brilliant reflectivity, making them one of the brightest features in the solar system when seen from afar. Embedded within the rings are narrow gaps, wave patterns, and ringlets shaped by gravitational resonances. The rings are dynamic, ever-changing structures, sculpted ice caught in motion. Ceres is both an asteroid and a dwarf planet. Located in the asteroid belt between Mars and Jupiter, Ceres is the largest object in that region, so large, in fact, that it qualifies as a dwarf planet. Discovered in 1801, Ceres is spherical, unlike smaller asteroids, and may contain a subsurface layer of briny water or mud. NASA's Dawn spacecraft revealed mysterious bright spots on its surface, which turned out to be deposits of salt, possibly left behind by evaporating water. Ceres is a hybrid world, neither quite planet nor typical asteroid offering, a glimpse into the early ingredients of planetary formation. Mars appears red because of rust. The surface of Mars is coated in a fine dust of iron oxide, the same compound that gives rust its color. Over billions of years, this iron-rich material has oxidized in the thin Martian atmosphere, creating the planet's signature reddish hue. The dust is so pervasive that it colors the sky during storms and coats the entire planet. Despite the rusty appearance, Mars also has dark basaltic plains and polar ice caps, creating subtle color variations across its surface. But from a distance, that distinctive reddish tone dominates, a dusty signal of oxidation on a cold desert world. Sunspots are cooler regions on the sun's surface. Though the sun's surface blazes at thousands of degrees, some areas appear darker, not because they're cold, but because they're cooler than their surroundings. These are sunspots, temporary regions where intense magnetic activity suppresses the outward flow of heat. Sunspots can be larger than Earth and often appear in pairs or clusters. They follow an 11-year cycle, growing more numerous and active as the sun approaches solar maximum. Despite their name, they are still extremely hot thousands of degrees, but the contrast makes them appear dark. These spots are magnetic scars, revealing the sun's ever-changing internal currents. Uranus was discovered by telescope. Unlike the planets visible since ancient times, Uranus wasn't officially identified until 1781, when astronomer William Herschel observed it through a telescope. At first, he thought it might be a comet or star, but further observations confirmed its planetary motion. Uranus became the first planet discovered in modern times, expanding the known boundaries of the solar system. Its discovery marked a shift from naked-eye astronomy to instrument-based exploration. Since then, Uranus has revealed many surprises, from its extreme axial tilt to its faint rings and icy moons. It's a planet that quietly rewrote the map of the night sky. The solar system is about 4.6 billion years old. By studying ancient meteorites, radioactive isotopes, and the oldest rocks on Earth and the Moon, scientists have traced the age of the solar system to around 4.6 billion years. It began as a swirling cloud of gas and dust, a solar nebula, which collapsed under its own gravity, forming the sun at its center. The remaining material coalesced into planets, moons, asteroids, and comets. This process of accretion and differentiation laid the foundation for everything that followed. The planets we see today are survivors of a chaotic beginning, shaped by collisions, migrations, and long, slow cooling. Vesta has a layered structure like a planet. Vesta, the second largest object in the asteroid belt, is not just a rock. It's a protoplanet with differentiated layers. Beneath its surface lies a mantle and a dense metallic core, similar to the internal structure of Earth and other terrestrial planets. This means Vesta once had enough internal heat to melt and separate into layers, a process called planetary differentiation. The giant impact that carved out the Rhea Silvia crater at its south pole may have exposed some of these deeper layers. Vesta is a frozen fossil, a planetary building block that never quite made it to full planet status. The Moon has quakes. Though it appears still and silent, the Moon occasionally trembles. These moonquakes can be caused by tidal forces from Earth's gravity, thermal expansion as the lunar surface heats and cools, or even meteorite impacts. Some quakes originate deep within the Moon and can last for up to an hour far longer than earthquakes on Earth. Data from the Apollo missions first revealed these subtle shakes, and new instruments continue to study them. Though the Moon has no tectonic plates, its quakes suggest an interior that is not entirely dormant, a solid world with a quiet, pulsing heart. Triton is a captured moon. Neptune's largest moon, Triton, is unique among major moons because it orbits in the opposite direction of its planet's rotation, a retrograde orbit. This unusual path suggests that Triton did not form around Neptune, but was captured from the Kuiper Belt long ago. The gravitational disruption from this capture may have destroyed Neptune's original moons and heated Triton's own interior, causing tidal heating. Today, Triton has geysers that spew nitrogen into space, a thin atmosphere, and a frozen surface marked by strange cantaloupe-like textures. It is both a relic of the outer solar system and a moon shaped by a violent adoption. Neptune has 14 known moons. Neptune, the The farthest major planet from the Sun is orbited by at least 14 moons, ranging from large and mysterious to small and irregular. The largest, Triton, makes up most of the mass, but others like Proteus, Nereid, and Larissa follow eccentric and varied paths. Some are likely captured Kuiper Belt objects, while others may have formed from collisions or debris. Most of these moons are icy and dark, reflecting very little sunlight. Their orbits offer clues about Neptune's violent past and possible planetary migrations. Together, they form a scattered family of companions around a planet that drifts on the solar system's distant edge. The Parker Solar Probe is touching the Sun. Launched in 2018, NASA's Parker Solar Probe is the first spacecraft to fly directly into the Sun's outer atmosphere, known as the corona. It moves at extraordinary speeds, faster than any object ever built, and endures temperatures of over 1,000 degrees Celsius. Protected by a carbon composite heat shield, the probe dips closer with each orbit, gathering data on solar wind, magnetic fields, and energetic particles. Its mission is to solve long-standing mysteries, like why the corona is hotter than the Sun's surface and how solar flares accelerate. In a sense, it is not just studying the Sun, it is flying through it. Some meteorites on Earth came from Mars. Though Mars is millions of kilometers away, pieces of it have landed on Earth. These are Martian meteorites, fragments of rock blasted off the surface by powerful impacts, which then traveled through space and eventually fell into our atmosphere. Scientists identify them by comparing their chemical makeup to data collected by Mars rovers and orbiters. Some of these meteorites contain tiny bubbles of trapped Martian air and minerals shaped by water, offering direct clues to Mars's geological and chemical history. These wayward stones are samples from another world, sent to us by nature long before any spacecraft returned the favor. The Sun is mostly hydrogen and helium. About 70% of the Sun's mass is hydrogen, and most of the rest is helium. These two lightest elements dominate its makeup and fuel the nuclear fusion at its core. Under extreme pressure and heat, hydrogen atoms are fused into helium, releasing vast amounts of energy. The remaining 1 to 2% of the Sun's mass includes oxygen, carbon, nitrogen, and heavier elements, all of which originated in earlier generations of stars. Despite its brilliance and complexity, the Sun is fundamentally simple in composition, a glowing sphere of primordial gases shaped by gravity and nuclear fire. Earth's tilt is as seasons. Earth's axis is tilted about 23.5 degrees relative to its orbit around the Sun. This tilt is the reason we experience seasons. When one hemisphere is tilted toward the Sun, it receives more direct sunlight and longer days, resulting in summer. When tilted away, the sunlight is weaker and days are shorter, bringing winter. Without this tilt, seasons would barely exist, and most of Earth's climates would be far more uniform. The tilt has shifted slightly over time due to gravitational influences from the Moon and other planets, but it remains one of the quiet architects of life's seasonal rhythms. Jupiter's magnetosphere is the largest structure in the solar system. Jupiter's immense magnetic field extends millions of kilometers into space, forming a magnetosphere so vast it would appear larger than the Sun in the night sky if it were visible. This field is powered by electric currents in the planet's metallic hydrogen interior. Within the magnetosphere, charged particles zip along magnetic lines, creating intense radiation belts, massive auroras, and fierce electrical storms. The field captures particles from Io's volcanic eruptions and shapes the orbits of nearby moons. For spacecraft, the radiation here is a major hazard. For scientists, it's a laboratory for studying planetary magnetism at its most extreme. Planetary rings may be temporary. Though they appear timeless, planetary rings like those around Saturn, Jupiter, Uranus, and Neptune may be relatively short-lived on cosmic timescales. Rings form from shattered moons, leftover debris, or icy particles pulled into orbit. But over millions of years, these materials can spiral inward due to gravity, magnetic drag, or collisions, eventually falling onto the host planet. Observations suggest Saturn's rings may be less than 100 million years old and could vanish within another 100 million. The rings we see today may be a fleeting phase, a spectacular, shimmering moment in a planet's much longer life. The moon's surface barely changes over time. Without wind, rain, or active geology, the moon's surface remains almost entirely unchanged for millions, even billions, of years. Footprints left by astronauts will likely remain preserved for thousands of generations. Micrometeorites and cosmic radiation are the main forces that slowly wear down the lunar landscape, causing a gradual erosion known as space weathering. Craters from ancient impacts still dominate the terrain, creating a record of collisions going back to the solar system's earliest days. The moon is not only Earth's closest neighbor, but also one of its oldest and most faithful geological archives. Some icy moons may have hydrothermal vents. Beneath the icy crusts of moons like Europa and Enceladus, scientists believe subsurface oceans may touch hot, rocky cores, forming hydrothermal vents similar to those found on Earth's ocean floor. On our planet, such vents support entire ecosystems without sunlight, using chemical energy from minerals and heated water. If similar vents exist on these moons, they could provide the conditions necessary for life: water, heat, and a steady energy source. Plumes from Enceladus even contain compounds associated with biological processes. These hidden underwater worlds may be the most promising places to search for life beyond Earth. Sunlight takes over 8 minutes to reach Earth. Light that warms your skin and brightens the sky began its journey in the sun's core, where nuclear fusion creates photons. These photons then take hundreds of thousands of years to travel from the sun's center to its surface, bouncing and scattering through dense plasma. Once they escape the surface, however, they travel the remaining distance to Earth, about 150 million kilometers, in just over 8 minutes. When you watch a sunrise or look at the midday sun, you're seeing it not as it is, but as it was 8 minutes ago. A glimpse into the very recent past. Europa's cracked ice may shift like tectonic plates. The surface of Jupiter's moon, Europa, is covered in a shell of ice, crisscrossed with dark lines, ridges, and chaotic terrain. These features suggest the ice may be moving, breaking, sliding, and even subducting like Earth's tectonic plates. If true, Europa would be the only known body besides Earth with active plate-like motion. The process could help cycle nutrients between the surface and the ocean below, increasing the moon's habitability. The driving force is likely tidal flexing from Jupiter's gravity, which continually needs Europa's interior. It's a frozen world, but not a static one. Saturn is less dense than water. If you could place Saturn in a giant cosmic bathtub, it would float, not because it's hollow, but because its average density is less than that of water. Saturn is composed mostly of hydrogen and helium, giving it a lightness despite its massive size. Its volume is enormous, more than 700 times that of Earth, but its mass is only about 95 times greater. This low density gives Saturn a gentle, diffuse structure, with rapid rotation that flattens it at the poles and bulges it at the equator. It's a giant of gas, softly puffed into shape by gravity and motion. Solar flares can disrupt technology on Earth. Solar flares are sudden, powerful eruptions of energy from the sun's surface, often linked to sunspot activity. These outbursts release intense bursts of radiation across the electromagnetic spectrum, including X-rays and ultraviolet light. When directed toward Earth, they can disturb the upper atmosphere, affecting GPS systems, radio communications, and satellite operations. In extreme cases, they can trigger geomagnetic storms, potentially damaging power grids. While Earth's magnetic field offers protection, flares remind us that the sun is not a steady light bulb, but a dynamic, volatile star, one that occasionally sends ripples of energy pulsing across the solar system. The solar cycle influences auroras. Auroras, the shimmering curtains of green, red, and violet light near Earth's poles, are caused by charged solar particles interacting with Earth's magnetic field and atmosphere. These displays become more frequent and intense during periods of high solar activity, which follow an 11-year cycle. During solar maximum, increased sunspot activity and solar flares send more particles hurtling toward Earth, fueling brighter auroras. During solar minimum, the lights are quieter. The sun's magnetic fluctuations ripple outward, and we see them in the skies, a reminder that space weather can paint the heavens in subtle solar brushstrokes. Comet tails always point away from the sun. As a comet approaches the sun, its icy surface begins to sublimate, releasing gas and dust that form a glowing tail. But contrary to intuition, the tail doesn't trail behind the comet like smoke behind a train. It points away from the sun, no matter which direction the comet is moving. This is because solar wind and radiation pressure push the material outward, forming two distinct tails, a curved dust tail and a straight bluish ion tail. The result is a luminous, windswept signature, tracing the invisible force of sunlight through the darkness of space. Some planetary moons formed from giant impacts. Earth's moon is believed to have formed from a colossal impact between the early Earth and a Mars-sized body over 4 billion years ago. The collision ejected material into orbit, which gradually coalesced into the moon. Similar impact origins are suspected for other moons, such as Pluto's Charon. These violent beginnings contrast with the captured moons of the outer planets, showing that no single process explains all satellites. Some moons were born of fire and collision, others from gentle gravitational snaring. The diversity of their origins mirrors the chaos and creativity of the solar system's formative years. Voyager 1 carries a golden record into deep space. Launched in 1977, Voyager 1 now travels through interstellar space, farther from Earth than any other human-made object. Attached to its side is a golden record, a phonograph disc containing sounds and images chosen to represent life on Earth. It includes greetings in dozens of languages, music from around the world, and recordings of waves, birdsong, and laughter. Designed by a team led by Carl Sagan, the record is meant for any intelligent beings who might someday find it. It's a message in a bottle cast into the galaxy, a quiet greeting from our pale blue dot. Earth shares its orbit with co-orbital asteroids. Although Earth orbits the Sun alone in its path, it shares its general region of space with small bodies known as co-orbital asteroids. These objects don't orbit Earth like moons, but instead follow stable, looping paths near Earth's orbit, shaped by gravitational interactions. Some, called Trojans, hover around stable Lagrange points ahead of or behind Earth. Others follow horseshoe-shaped paths that keep them near but never colliding. These quiet companions are often temporary, captured and released over thousands of years. Invisible to the naked eye, they drift near us in space, fellow travelers on our yearly journey around the Sun. Neptune was once confused with Uranus. Before Neptune was officially discovered in 1846, some early astronomers may have observed it without realizing what it was. Because it moves so slowly and appears so dim, it was occasionally mistaken for a fixed star, or thought to be another sighting of Uranus. In fact, Galileo may have unknowingly seen Neptune through his telescope in 1612 and marked it as a star. It wasn't until mathematicians noticed irregularities in Uranus's orbit that Neptune's existence was predicted and confirmed. In a sky filled with wandering points of light, Neptune remained hidden in plain sight for centuries. The edge of the solar system isn't defined by gravity. The Sun's gravitational pull extends far beyond Pluto, holding on to distant comets and icy bodies in the Oort cloud. But when scientists speak of the edge of the solar system, they often refer to the boundary of the heliosphere, the region where the solar wind meets the interstellar medium. This edge, called the heliopause, marks the point where the influence of the sun's magnetic field and particle flow ends. Gravity continues far beyond, but the energetic boundary is where the space between stars begins. It's a subtle, shifting frontier, more a change in pressure than in presence. Planetary atmospheres slowly leak into space. Even thick atmospheres like Earth's are not permanent. Over time, light gases like hydrogen and helium can escape a planet's gravity and drift off into space. This process, known as atmospheric escape, is more pronounced on smaller planets with weaker gravity, such as Mars and Mercury. On Venus, a lack of magnetic shielding has allowed the solar wind to erode parts of its upper atmosphere. Earth loses thousands of tons of hydrogen each year, though it's easily replenished. The slow escape of gases is a quiet leak into the void, a constant exchange between planets and the vacuum beyond. Some moons may have formed from ring systems. Just as ring systems can decay into planets or vanish over time, they can also give birth to moons. In Saturn's case, it's possible that some of its small, outer moons originally coalesced from ring material that clumped together beyond the Roche limit, the boundary beyond which gravity can pull matter into moons rather than tear it apart. Moons like Pan and Daphnis, which orbit within Saturn's rings, may still be accreting material from them today. These moonlets serve as quiet sculptors of the rings, their gravity carving gaps and waves into the icy bands around them. Voyager 1 is still sending data from interstellar space. More than 45 years after its launch, Voyager 1 continues to transmit faint signals back to Earth, even as it travels through the interstellar medium billions of kilometers from home. Its instruments measure cosmic rays, magnetic fields, and plasma density in the space between stars. Power is limited, and systems are gradually being turned off to conserve energy, but the spacecraft still functions. It uses a tiny nuclear power source and communicates via the Deep Space Network. Every signal takes more than 20 hours to reach Earth, a whisper from the edge of human exploration. The solar system completes a galactic orbit every 225 million years. While the planets orbit the sun itself is also moving, revolving around the center of the Milky Way galaxy. It takes roughly 225 to 250 million years to complete one orbit, a journey sometimes called a cosmic year. During that time, the solar system drifts through different regions of interstellar space, potentially passing through galactic arms, star-forming regions, and clouds of gas and dust. This motion may influence comet activity, and on longer timescales, even Earth's climate. We are not fixed in space, but part of a vast, slow spiral, riding the galaxy's arm like a cosmic carousel. And so, our quiet journey through the solar system comes to a gentle close. From the inner world scorched by sunlight to the icy moons that whisper in the dark, we've wandered together through orbits, storms, and shadows, one sleepy fact at a time. If your eyes are already heavy, that's just fine. Let the last traces of starlight fade behind your thoughts, and let your breath carry you softly into rest. There's still so much more to discover, but for now, you've learned enough. You've traveled far, and the universe can wait until morning. Thank you for spending this time with me. And so, under the quiet stars, the story continues. I hope you sleep well and dream softly. Good night.